Hello everybody, so this is Bite Size Chemistry Part 3 and we're looking at chemical bonding and VSEPR shapes and so forth. So 2013 question 10A is what we're looking at first, and you're asked to distinguish between intramolecular bonding and intermolecular forces. But whenever you're asked something along these lines, all you have to do is to define both. So intramolecular is forces within a molecule, okay, the emphasis on the word within. And intermolecular forces is forces between molecules. And again, emphasis on the word between. Okay, this is really important. Okay, sometimes some of my students get these mixed up. So I always remind them there that if you look at the E in inter, there's an E in between, there's an E in inter, there's no E within. Okay, so that might be an easy way for you to remember it at the beginning at least. Okay, so just for that one there. And you can see I have part 3 answered already, so I'm just going to move that down, and I'll get to that now in 2 moments. So let's get on to part I. I says the boiling point of hydrogen, which is 20 Kelvin, is significantly lower than that of oxygen, which is 90.2 Kelvin. Okay, and you're to explain in terms of intramolecular bonding or intermolecular forces or both why this is the case. So why is hydrogen significantly lower than that of oxygen? Well, it comes down to molecular mass, their relative molecular mass. Okay, so hydrogen is smaller, which is a lot smaller than oxygen. Hydrogen is a lot smaller than oxygen. Okay, this generally means that smaller an atom is, the less likely the bonds are going to form. Okay, and less likely bonds to form, the weaker they're going to be. Okay, so hydrogen is smaller than oxygen atom, more likely to be van der Waals. Now, you could be wondering there, how did I go to intermolecular forces there, opposed to intramolecular forces? Okay, well, in this case here, if you're ever looking for boiling points, everybody, boiling point specifically goes towards intermolecular forces. So that's van der Waals, dipole-dipole, or hydrogen bonding. Okay, now we're not dealing with water, we're only looking at hydrogen here, and we're dealing with oxygen here. So hydrogen is a lot smaller than the oxygen atom, okay, and therefore it's more likely to be van der Waals. Okay, or to specify there, not even more likely to be van der Waals, more likely to have weaker van der Waals. That's what I should be saying. To have, because oxygen could also, probably does actually for that matter, have van der Waals bonding as well. So more likely to have weaker van der Waals. Okay, sorry, I should have specified that at the start. Okay, the word weaker there. Okay, so more likely to have hydrogen is a lot smaller than oxygen atom, and therefore it's more likely to have a weaker van der Waals forces. That's it. Okay, we're done. Next one. So that was part I. Part II is asking you, iodine has a very low solubility in water. Okay, so how do we go about answering that? Well, solubility. Solubility has to do with polar or non-polar. Okay, that's where it comes down to. Okay, and like dissolves like. So water is polar. You have to learn that one off, guys. Or you can check the electronegativity values. So water is polar. Therefore, iodine, if it has a very low solubility, must be non-polar covalent. I can spell today. Non-polar covalent if solubility is low. Okay. If iodine was polar, it would readily dissolve in water. But the question says iodine has a very low solubility in water. Water is polar, iodine must be non-polar, and covalent if solubility is low. Okay, and that's it. We leave it at that. Okay. Anything else to say on it? No. Okay, just that you must say both. You must specify that water is polar, and you must specify that iodine is non-polar. Next, for part 3, and I have this one answered already. When a charged rod is held close to a thin stream of water flowing from a burette, the thin stream of water is deflected. So you might have done that experiment at home, or you might have done it in school. So, why is this the case? Well, the charge on the rod attracts the opposite charge on the water, which is polar. So if something is polar, it means we'll have a partial charge. They're what we call the dipoles. Okay. So what happens there is when we charge a rod, what we're doing is we're removing or adding electrons depending on what material we're using and what type of rod it is and so forth. But either way, there is going to be some sort of attraction and deflection occurring, and usually deflection. So what happens there is the charge in the rod attracts the opposite charge on the water, which is polar. And when it does so, it actually deflects the water, okay, a small bit, because it's attracting the opposite charge. Okay, now if you don't know that, guys, honestly, I wouldn't be worrying about it too much. I would just learn that one off. Okay, it has come up before, and we're probably going to come across another question with it soon enough. But really, I would learn it off for that. Okay, because the answers are generally the same. If you just learned that off, you'll be fine. Okay, let's look at 2011. So this is question 11 actually, part B. Okay, so distinguish between ionic and polar covalent bonding. So ionic is forces of attraction between oppositely charged ions. You have to turn it off. This definition doesn't come up too often. It can appear in question 4. And polar covalent bonding? Well, polar covalent bonding is the unequal sharing of electrons. So therefore you have a dipole present. Now, why do ionic substances conduct electricity when molten or dissolved in water, but not in a solid state? So what's happening there? Well, when they're in a molten or dissolved state, okay, the ions are free to move. So that's what you say. Ions are free to move. And if they're free to move, they're free to pass on their electrical charge. Okay, free to move, whereas, and you must specify, solids, the ions are locked. That means they can't move. They're locked in position, we'll say. Okay, they can't move. And that's it. So they conduct electricity when molten because they're free to move, but if they're a solid, they're locked in position, or sometimes you can say they're fixed. Okay. Part 3. So part 3 is asking us there about ammonia, which we've seen a few times now at this stage. Ammonia being NH3, you have to turn it off, but you're told it's here anyhow. Show that ammonia has a polar covalent bonding. Well, if you want to show if it's polar covalent or non-polar covalent, or even ionic for that matter, so if you're not sure, we go back to those electronegativity values. So we have nitrogen here, we have hydrogen here. So hydrogen is 2.1, I remember that. And nitrogen, I'm just going to flick back up here because I lost my place. Nitrogen is a 3. Okay, I lost my electronegativity log tables there. I was reload them again. So look, 3 minus 2.1, okay, is 0.9. Therefore, NH3 as ammonia is polar covalent. Full marks. Okay. Now, you must show that NH3 has polar covalent bonding. Okay, so now we know it has it. Now we must show it. So we put our N up here, and we put in our lone pair, of course. Dot there, dot there, dot there, and put in our hydrogens. Okay, grand. Now we must show it by means of a dipole charge. Now, a couple of ways you can do this, guys. Okay, you can do it per bond if you want. So you can just specify there that we're looking at nitrogen and hydrogen, like this. You can leave it like this if you wanted to, and just go delta negative, delta positive. And the reason nitrogen is negative is simply because it's more electronegative than hydrogen. So therefore, it has a negative charge because the electrons are closer to nitrogen at any one time compared to that of the hydrogen. So that's all I have to say for this. Okay, you didn't need to draw it in this overall. It wasn't necessary. You could if you wanted to, but just take out a bond, because that's what we're talking about, covalent bonds, a single covalent bond, and you're grand. Lots of students try to draw this out and they get confused then with the deltas. So ignore that and just draw out your bond and you'll get full marks. Okay, so all I had to do was draw this, and you had to show this. Okay, if you drew this and the examiner thought you were having a guess or whatever, okay, you might not get the marks. So I always recommend students to do it out, all out, just to be sure. Okay, it's not worth chancing it to get some of the marks. So the last part there is describe the process involved when ammonia dissolves in water. So if it's dissolving in water, this has got to do with your if it's polar covalent or not. Now, ammonia is polar, like dissolves like, so therefore ammonia, NH3, will readily dissolve in water, okay, which is also a polar substance. Okay, so what happens there? I'm just going to do it out over here. I know it's not IV, but I just want to make a heading verse, that's all. Okay, so describe what's happening here. Nitrogen and hydrogen form a hydrogen bond, and we can specify that as intermolecular. So form a hydrogen bond, and that's it. Okay, from a hydrogen bond, you could specify that nitrogen has a negative dipole and hydrogen has a positive dipole. Opposites attract. And that's it. Okay, something along those lines. Okay, and you'll get your marks. Okay, so next, that was 2011. Let's move on to 2010. How many have we got left? Got 2 more after this. Yeah, we might do this on this video. We'll see. 2010 is short enough. Okay, so this was part A, question 10. State which of the following has hydrogen bonds. I, part 3, and justify your answer. Okay, so hydrogen chloride is HCl. Okay, and remember, hydrogen bonds need hydrogen and what am I thinking of there now, guys? And nitrogen, oxygen, or fluorine. Okay, so grand. Water, H2O. Is oxygen present? It is. Okay, so water is going to be fine. Ammonia, NH3. Is nitrogen present and hydrogen present? Yes, it is. So therefore, H2O and NH3 feature hydrogen bonding, and then you specify why. Okay, for both of those, hydrogen bonds to nitrogen, oxygen, fluorine for hydrogen bonding, and you get your full marks. Okay, so there's 9 marks going for that. You got 6 marks for identifying which compounds feature hydrogen bonds, and then you got 3 marks then for your reasoning behind it. Next, suggest a reason why the boiling point of ammonia is significantly lower than that of water. Okay, so students get confused with this all the time. They think because there's hydrogen bonding, there's going to be incredibly high boiling points. Well, this isn't necessarily the case. Ammonia also has hydrogen bonding, and it's quite low, a boiling point of minus 33 degrees. It's only for when you're comparing it to that of hydrogen bonding to that of dipole-dipole or van der Waals that it's much greater. Okay, water is quite high anyhow. Okay, so just to bear that in mind. Okay, that the boiling points can vary. They don't always necessarily have to be very high. Okay, so you're asked to suggest a reason why ammonia is lower. Okay, well, You can check your electronegativity difference. That's what we're going to do. And we'll do our H2O. So that's our NH3. So we have our nitrogen is a 3. Oxygen, oh, I'm doing it on the wrong one. So hydrogen is 2.1. Oxygen is, I'm not sure, I'll have to check it up now in a second. But nitrogen is a 3 and hydrogen is 2.1. So difference is 0.9. Okay. So 2 seconds there, and now electronegativity table there is what I want. Electronegativity table. Okay. Okay, I have oxygen here now, guys. So oxygen, if you're looking at it there, is 3.5. So you get the difference of that. Then, and again, use a calculator if you want. It doesn't really matter. Okay, it's 1.4. Okay. The greater the electronegativity difference, guys, the more for hydrogen bonding in here, the higher the boiling point. So the greater the electronegativity, dy, the stronger the bonds, therefore the higher the boiling point. The stronger the bonds, the more what's the word I'm looking for? The higher the boiling points. Okay, so that was fine for that one. So all I need to say for that was the electronegativity difference there was greater for water than it is NH3, and the greater the electronegativity difference, I suppose. See, the stronger the bonds, and therefore the higher the boiling points. Okay, so that's 2010 done.